we're waiting for this grand moment. Oh yeah, very good. So, good morning for the third time. I hope you had enough time to digest a little bit the lecture of yesterday. So first of all, I just wanted to ask you whether you have some curiosity or question about what we said yesterday, something you want to ask me. Many of you came after the lecture to ask things. This seems not to be the case. Just recall that we were just in this little trip, in this little detour, to make some guaranteed use of your time in these lectures. So we studied the missing. I always have this problem with missing. Is it with one or two S's? Two, thank you. So the missing S. So the missing meson problem. The missing meson problem, something real. So this was a problem and it was solved. So you have learned something that is useful. You know, with Axions, we don't know whether they exist or not, right? So at least this you have. But I told you that this will be solved by Toft instantons and the anomaly. So this is the solution. This is also real, so quite profitable. And this introduces the strong CP problem, which I don't like calling a problem. So I will call it a strong CP issue, as frequent as I can remember, because the trend to call it a problem is really strong. And then we're talking about the axiom, right? So we are out of these 4 items, at least 3 of them have something to do with reality, as far as we know. And okay, so yesterday in the end of the lecture, I told you, okay, what do not problem about the missing meson problem, because the transformations corresponding to a common phase of all the quarks, those who are related with the U1 axial transformation, they are not symmetries. Okay, these transformations this symmetry is very strongly violated by the color anomaly. And I also wrote you this, right? This equation that tells you that the quark masses, we never doubted that there would be this term here, minus 2m down, because this is a violation that is I already told you about, right? I told you the quark masses transform under this symmetry, right? So they cannot be, so they have to violate the symmetry, so the divergence of the nether current cannot be 0. But there's also another term here that has to do with the anomaly, okay? And I show you this, that has to do with these triangle diagrams, or the fact that the measure in the path integral does not transform trivially under these phase equations, okay? So this is not invariant under U1. This triangle diagram, somebody asked me, so it seems that it is not so clear what I said. The idea is the following. So here you really put this operator here. This operator, remember that it was, or the current, the axial current, is a bilinear in the quark fields. So this object has some quark coming in and some quark coming out. So what is running in this loop are just quarks in this case, right? That's why you can just produce gluons, of course. So quarks are here, So you have up, and then the axial current. You have plus, down. I read explicitly here all the terms. So if I put this operator here, computing the divergence, I can put this operator here, right? I can compute this loop. And if this would be if this doesn't exist, so I should be able, if this would be the whole story, it should be the same to compute this loop using the divergence of the current, so this operator with the divergence, or simply this operator, right? Which you can call J5, or this combination of operators. Should be the same to put J5 with the masses, or the divergence of the current, but it is not. That's the anomaly, okay? So this equality is violated at the quantum level by this term, by this unique loop. And actually, this equation is just true to all orders. That's a very interesting and very important point. So there is, I'm sorry, I'm going to continuously abuse notation. So GG tilde is the contraction of the field strength tensor of the gluon with its dual. And it is the new term that comes in this lecture, although you already had it in the previous lecture. So let me just tell you a couple of things of this object, which are quite important, right? So first of all, sorry, by the way, I repeat again what I said yesterday. How does this solve the missing meson problem? Well, remember, so if you have some term that violates the symmetry, it will give mass to the Goldstone bosons that are associated with the spontaneous breaking of that symmetry, right? And actually, we computed the mass that these terms give to the pions and the eta. Okay, this we did. Now I'm telling you that there is another term here that violates this symmetry. So you have to think that there will be another term, another mass term. So in particular, the Goldstone boson associated with this symmetry will have an extra mass coming from this breaking, if you want to think about this. Actually, this breaking is so strong that sometimes people, or not sometimes, it is a matter of debate whether you would call eta prime a Goldstone boson at all. Okay? But here I'm going just I find it much easier to just don't go into very subtle issues here. I think it's much easier to exploit the parallelism between the eta prime and the rest of the Goldstone bosons. And you can just think that because I'm breaking with another term the symmetry, I'm going to get an additional mass in the potential, and this is going to solve the missing meson problem. And this new term is going to be generated by this object, this GG tilde, that sometimes I will with the indices and sometimes not, because I mean it's uniquely determined. This is the gluon field strength contracted with itself via the epsilon tensor. And this is a very interesting object that first of all violates parity and time reversal. I think you I told you yesterday, Alex Pomarol already told you this, right? And he said, this is very simple because you have always the epsilon tensor. So one of these indices is always going to be time, and the rest are going to be space, right? And but I think he didn't explain much more. So do you all see that this violates parity and time reversal? Yes? You seem quite... actually, this is going to be a relatively hard lecture for 9 in the morning. I'm telling you. I'm sorry for that, but this is what it... they didn't think about that when they made the schedule. Well, so the idea is that, yeah, epsilon is always 0, 1, 2, 3. So this means that these objects, the field strength tensors, they are always going to be something like this, G01, G23. This, the field strength tensor involves derivatives, or one derivative, right? And the other index is for the gauge field. So when you make a parity transformation, all the space indices flip a sign, right? So the A field is also going to flip a sign. So this will, this guy under a parity transformation will change sign, and this gentleman here will change two signs, so it will not change anything. So you will have a plus and minus. So this will give you an overall minus sign. So this actually, this object changes parity maximally, right? From plus to minus. And under a time reversal, you see the same, right? The index with 0 is a derivative with respect to time. So if I change the sign of time, this gets a minus. This doesn't change, and this doesn't change. So this gets an overall minus. So if you do a parity transformation, or if you do a time reversal transformation, this object, because of the derivatives, changes sign. Okay. So this is going to introduce potentially violation of parity and violation of time reversal. And since you know that in quantum field theory is a quite general result that CPT is conserved, so sometimes we abuse. We don't abuse the language, and we just say that this object also violates CP. And this is what creates the strong CP, the name of the brand name of the strong CP problem. So this is the concept. So this object violates parity and time reversal. That's interesting. So, but this is very unwelcome news, because our original motivation to build QCD, or to accept QCD as a theory of the strong interaction, was that it was respecting parity and time reversal, because they are not observed in the strong interactions. Okay. Very good. More bad news is that this object is a total derivative. A total derivative that I can never remember. But perhaps it's not that important. I don't even have it. But okay, but this is for you to know. You don't have to copy it also, because I didn't write it so nicely. But this is, I mean, in a sense, you can just reorganize the derivatives here to build it this way. Okay. The important thing is not the particular form now. I'm not going to make use of this formula explicitly myself. So whenever we need it, I would just tell you what the result is. The important thing is that because of this particular issue, when we encounter integrals of this operator with the adequate powers of the coupling constant, that I'm not going to bother you very much with the coupling constant here. It's going to disappear. So this, in principle, is, you can just use the Gauss theorem to convert this into a surface integral of this current, right? This is the divergence of a current. So just change this for a hypersurface integral of this current. And this means, well, now if I just, I'm interested in integrals of gauge fields which go smoothly to 0 at infinity. So because I'm interested in local things, I say that, okay, if I'm interested in gauge fields that go to 0 at infinity. So this should be 0. And this is a bit of a problem. And it actually has, so this is the this is the main reason why this term was never, well, was not taken very seriously, or was not discussed before Toft decided to look a bit more closely into the structure of these Young-Mill theories and the problem of the anomalies. Very good. So there are these three things. If this term is non-zero, or the integral is non-zero, there's a strong suspicion that this is going to generate a mass for the eta prime. These are the three things important here. And very good. So I'm going to tell you why this G tilde is actually different from 0. This is a rather abstract part of the lecture, so bear with me. So the reason why this G tilde is not 0 is because of a subtle aspect of Young-Mill theories, which is the definition of vacuum, okay? The QCD vacuum. In this case, the QCD vacuum is highly non-trivial. So one would think, so what would be the natural vacuum for a gauge theory would be simply to just take the gauge fields to 0, right? This would be my favorite vacuum, right? However, this is not the end of the story. One can just consider gauge transformations of the vacuum, okay? So in order to deal with this, it is customary to define a gauge field which is contracted with of SU3, okay, which are the Gell-Mann matrices, and one defines this object here, which is an object of the Lie algebra of the SU2. So this is a matrix, okay? Now, have you ever heard about? You all have had lectures on Young-Mill theories, right? So if I ever say something which is very weird, you just stop, point your head upwards, stop and ask. But you have not had any lecture on the vacuum structure of Young-Mill theories, no? Right? Okay. So there we go. So one can ask whether so if I just take this very reasonable vacuum and I apply gauge transformations to it, are all these vacua equivalent, or just are they all trivially equivalent in a sense? And there's a very subtle issue about all the gauge transformations that one can make to 0, and is that one can change the topological configuration of the gauge field. Okay, and this can be better seen by just kind of trying to construct these gauge transformations. So a pure, let me just see, a pure gauge configuration for the vacuum, okay, for this object, it can be written as, and this is where this is very interesting. So the way, so a pure gauge configuration is just given by objects of this type, which is essentially the gauge transformation from 0, right? So if I just gauge transform A equals 0, I have this omega is just an element of SU3, okay? That I want to apply my transformation onto, and this is the gauge part. So all the gauge transformation, they have to satisfy this form, and this is very interesting. This is already telling you that the gauge field no, not surprisingly, is so if you give me a transformation of SU3, I give you a different vacuum. Okay, so gauge transformation gives you a different vacuum. Now, are all these vacuum equivalent? And this is the funny part. Or this is the subtle part. So if I normally, so there are many possibilities for these transformations, but there are certain subclasses which are the non-trivial, and these ones are normally found by fixing partially the gauge, by just going to the temporal gauge. Okay, temporal gauge. Or let me just of all gauge transformations. The interesting ones for us have, or in this gauge at least, are the ones that go, by the way, yeah. So if we fix the gauge like this, we shall, you can probably remember that we can still have transformations that depend on space, right? So as long as my my gauge transformation does not depend on time, I'm not violating, I will not generate a zero component of this gauge field. So the interesting ones are the ones that go to 1 at infinity. All the rest, I think they can be classified as global transformations, and these are the interesting ones, where the topology is going to play a role. Why is this so? Because if you say that this function here, or this element of the Lie group, this element of SU3, has to go to the identity at infinity, this is like saying that all infinity points, they have the same value, right? So you can just, in a sense, if you want to study the topology, you can just think that infinity is the same point, right? So this is equivalent to this Riemann projection. So in one dimension, this is very simple to see, right? So you just, from each, you can just map a sphere into, or just a circle into the continuum, right, by the Riemann projection. So this would go to infinity. This point here, or this point here would go here, and so on. So just by fixing this point, you can just map points in the sphere to points in R. And this means that with this type of map, you can do it also in 3 dimensions, right? So now, yeah. So instead of defining my functions omega in R3, so in 3-dimensional space, now I can think that the configurations that I'm calling interesting are those who live in a 3 sphere. Okay, so this is just simply because we have imposed. This is just, I'm telling you that the rest are not so interesting, but these ones, they have some interest because they live in this sphere. So actually building these configurations, now you can think about it geometrically. All the possible configurations, they're just functions, so functions of that map the 3 sphere into SU3, right? For each point of the sphere, I get a function, I get a transformation of SU3, and then I can immediately build my gauge configuration, which is this, right? So that's the idea. So building a mu, which is equivalent in this gauge, is just building the 3 components, is just giving this field configuration, but this one is defined in the sphere. Okay? Now, the interesting thing is that is this piece here, right? So all the gauge, so the elements of SU3 that can be mapped in a sphere, they essentially they form classes, okay? They are called homotopy classes of transformations that cannot be converted into each other, right? And this you can see immediately. So this is SU3. Essentially, this prompts us to study the maps of S3 into SU3. Actually, this is equivalent, interestingly, to essentially to the maps of S3 and SU2. And so actually this is much easier to understand, because essentially SU2, so the parameters in SU2, right, live in S3, right? So these two things are essentially the same. Now, in order to understand these homotopy classes, let me just do the simplest example, which essentially is U1 in one dimension. Let's start with that, okay? Let's do it here. And you see immediately why these transformations, they form classes which are disconnected. So essentially, in the case of U1 in one dimension, right, it's just mapping one sphere, a circle, into U1. The elements of U1 are trivial, right? So they're just, you can just think them as faces. So it's how you define a phase field in a sphere. And here, you can just define, so you see immediately that there are classes which are differentiated by the number of times that the gauge field circulates when I go around the circle, okay? So let me just build it in a very simple way. So first of all, you have these kind of configurations that have more or less constant gauge fields, okay? So the element of U1 is the same in all the circle, right? And I can deform, so I can just, by changing smoothly my field, I cannot change the fact that this vector, okay, when I go around the circle, it doesn't move. So it oscillates like this, but it doesn't turn, okay? Now I have a second class in which when I turn, I have to write it like this. My gauge field is turning with me, right? So it's making a circle in the internal dimension. So in the gauge, in the space of the field configuration, or in the space of the group, okay, which is just faces, is just turning at the same time that I'm turning. Now clearly, this kind of configuration. So this would be. This is a map. This is this function, essentially, as a right? So what I'm writing there is just one function in a sphere. Instead of a three sphere, I'm writing it in one sphere and with a much simpler group. So you can understand. So the important thing is that here, this object cannot be deformed by smooth transformations into this configuration, okay? So locally, I can make all these vectors look very much like this, but by continuity, there will be always one small stretch of this circle in which I will do the full almost 2 pi, right? That's the thing. So these objects are not transformable into each other by smooth transformations, okay? So this is like the n equals 0 sector, n equals 1 sector, and I can write the n equals 2 sector by just with a little bit of work. So here a turn like this, right? And it's harder to draw than to conceptualize, right? You already, I mean, you understand perfectly what I wanted to write. Very good. So this is for U1 is clear. And what you see here is that the classes, so the classes of these disconnected gauge transformations, so I'm talking about disconnected in terms of topology, right? So I cannot change the topology of this map into this, right? So the number of these isolated type of maps is set, right? So it's just an integer. It's a infinite number of enumerable classes. So this happens, yeah. Actually, the same happens here in 3 dimensions. Although it's much more complicated to see. Sorry. So the way it's much more complicated to see because now you have to imagine a 3 sphere, which is already complicated, and then you have to put in each of the points of the 3 sphere, you have to put a gauge field, which in this description is a matrix, right? A 3-dimensional matrix. I'm just telling you that this is, so SU3, because SU3 contains in SU2, so this is the general idea behind this. SU3 contains SU2, so you can just think about one, so this SU2 that is inside of SU3, and forget about the rest of SU3. What I'm saying is that of all the Gell-Mann matrices that I can write here, you can just use the Pauli matrices. Okay, and the rest are not so important. So I mean, okay, the rest are not so important because actually one can prove that you cannot do more circles in this with the extra generators of SU3. Okay, in 3 dimensions, in the 3 sphere, you can do more. Sorry. This is the homotopy group of U1 1 sphere. And this is the homotopy group of SU3 into the 3 sphere. So this 3 is the sphere, this 1 is the sphere, and this would be the group. Okay? So So that's the result. It's not I'm not a super expert on this, but I can show you how these things look like. At least mathematically. I cannot draw this, and I've searched for hours in the internet in order to show you some nice graph of how these things could look like in some graphical representation. At the end, I think mathematics will do the trick. So let me just show you one of these objects. So I can just build the omega function, and I'm going to do it with SU2 because I told you that the rest of SU3 is not relevant in 3 dimensions. So the rest of SU3, so if you just perturb this solution with SU3 matrices, you can just take them to 0. Okay, this would be the idea. You can just expand this. You get something like that. So this is one example of such mappings, and here I'm just using a function r that is expressed in radial coordinates, and it goes from 0, and at infinity it has to go to some number. Okay, that's the idea. So that at infinity we have, so this is well, you say it immediately, right? So I have defined my interesting gauge configurations in such a way that they go to the identity at infinity, right? So this is what I'm getting here. Actually, I'm not going to 1, I'm going to exponential of e of exponential of e I times n times 2 pi, which is 1, right? And what you see here is that, so at infinity, of course, this function will go to 1, no problem. But it does so oscillating in different regions between 0 and infinity. It does things like first stays the identity, right? Like around 0 in this case, it will be the identity. Then it goes to this configuration, right? To this gauge matrix, where this x is just the unitary vector. Okay. So if I look in this direction, the gauge field looks like a rotation in the x direction. Okay. In this direction, it looks like a rotation along this direction, and in that direction, along a rotation in that direction. Okay. So remember that we are mapping SU2 matrices, which are, you can think as rotations, right, into a 3-sphere. So in the center, nothing. Then you move to a certain radius. This transformation, or this element of this omega function, this element of SU3, now looks like a rotation in this direction, like this, right? Like a spike. But then if you move a little bit forward, then it disappears. Okay. And so on. So it looks like a hedgehog that disappears, no, that oscillates from 0 to infinity. And it does, no, a hedgehog with a lot of vectors, right? So each of these vectors tells you one rotation, and every time you cross 2 pi here. So this is 2 pi, this is 4 pi. In this, at these distances from the center, the transformation is the identity. So the rotation is not rotation. So here you are always like rotating in SU3 in the direction of infinity. In each point, pointing to infinity, like this, like this, like this. If you cannot see, now, by the way, this, I've explained it very bad, I admit it, although nobody explained it like this to me. So normally people is quite happy with this thing, and they forget about the rest. So now you get a different picture. This hedgehog, where each of these vectors that is pointing to infinity is a rotation along that direction, right? And you see that how you are moving in this sphere, in this shell, and each point means a rotation in a different direction. So you get how the gauge transformation is rotating like this, right? And it does so many times from 0 to infinity. How many times? N times. So this n. Okay, so you don't have rotation, then you have one, then you have another, and so on. Good. So now we have classified all the gauge transformations of the vacuum, all possible gauge transformations of the vacuum. I told you that they can be classified into objects that have different winding number, right? And winding number is this n. This integer that tells you how many times you essentially you are wrapping the gauge field in your configuration from 0 to infinity. Oof. Questions? Thank you. Very good. So how does this change all this thing? Well, now when I want to so this is to make connection with what I've told you. Why are these things important? Because this object here is going to count precisely the amount of, so the winding number of the field of the gauge field. So this, remember, that this can be put as a surface integral of this vector, which is called the Chern-Simons current, and I can just in the A0 gauge, so the only component of the Chern-Simons current that is non-zero is K0. So integrating, so essentially this surface is an integration between 0 and infinity. So this is essentially, which I can do I'm doing explicitly when I integrate, when I do the gauge, the Gauss law. So this is essentially only the three-dimensional integral of K0 at time equal infinity minus so this thing what counts is the integral of K0, the spatial integral of K0 at plus infinity minus infinity. And what is this thing? Well, this thing is actually the so-called Pointryagin, or whatever it is pronounced. Pointryagin. Pointryagin. Have you ever heard about Pointryagin? How do you pronounce it? No? I will call it Pointryagin. And index, which is essentially the three-dimensional integral of this K0. I wrote it to you before, or the value of K0. And this is essentially the same n that I've told you before. This is a topological, or this is an integral that essentially counts how many times your gauge field winds in space from 0 to infinity. Okay? That's the important thing. So you see, this operator is non-zero. So it's non-zero, essentially. And these things were not discovered until Toft didn't have a close look at the vacuum of Young-Mill theories. Okay? Now, the important thing for us is that let us build a structure of the QCD vacuum to fix concepts with a picture. So we can try to write the QCD vacuum like this, or we can define a QCD vacuum that has n equals 0, a gauge field, a gauge configuration that has 0 energy. It's a pure gauge. Well, it's just the gluons equal to 0, has 0 energy. And then we have the sector of gauge configurations that have n equals 1. Okay. And what I told you is that these configurations, by the way, so since this is a pure gauge, also essentially it has the same energy than n equals 0. So these vacuum are really degenerate. This is the vacuum energy, or the potential energy of the vacuum. But these two, what we learned is that they cannot be they cannot be transformed into each other by, they cannot be distorted into each other, okay, by small transformations, by small continuous transformations or gauge transformations. Yep. This is, sorry, yeah. Remember, so for a gauge configuration, static, okay, we can define an n, which is the integral, if you want, from 0 to infinity of the configuration. How many times my configuration changes from 0 to infinity. This is a three-dimensional integral. If we do the four-dimensional integral, means integrate in time as well. And then you get the difference, okay? So both things are different, by the way. So, but it doesn't matter so much. So the Pontryagin index is just a three-dimensional integral, and this is the, is, of course, you are integrating here in radial coordinates to r infinity, right? So essentially it counts the number of times from 0 to infinity that the field wraps. Is a difference? Yeah, this is exactly this. Because here I'm talking about gauge configuration only. I'm not talking about transitions yet. But they are. No, sorry. No. This is radial coordinates. 0 to infinity is in radial coordinates. Oh.
I mean, you have the one that goes for t that t goes to plus infinity, right?
Yeah.
And then you have another index that goes t goes to minus infinity.
Yeah. So this is when I consider a gauge configuration. Oh, sorry. Yeah. Okay. It's super important to have these things clear. So I was talking about the vacua. Okay. So, and I told you that these are gauge configurations, okay? They are pure gauge configurations. And I was studying these pure gauge configurations in a particular gauge, the A equals 0. And then I told you that these are objects that do only depend on space, essentially, right? Right, so not forget about time there. And I can just, for a given moment of time, I have one of these configurations. I can define a gauge configuration that has 0 energy, but has particular winding number, right? Or Pointryagin index. So these are my vacua. And now, what I can do is to consider this integral okay, for any, essentially for any gauge configuration, okay? And this is equal to the, so this gives me essentially the Pointryagin index at plus infinity in time. So now this is for any gauge configuration. For any gluon configuration, okay? I get exactly the same integral that I got, that's the Pointryagin index. This is space, and this is space-time. Yeah, awesome. Here. Yeah, exactly. Exactly. So you get essentially, you get the number that, this is what I was just drawing this diagram. So you have different like vacua, and now you give me any gluon configuration that goes from minus infinity to infinity, and wherever it goes, it starts here and ends up around here. You calculate this integral, and you get 2 minus 0. So you get exactly the number of wrappings of the gauge field that you have experienced in that particular transition from minus infinity to infinity. Okay, that's the thing. The important something that I wanted to show pictorially here is that since you cannot transform smoothly with gauge transformations this vacuum to this, This doesn't mean that you cannot transform, of course, a gluon configuration from here to here, but it's going to cost you energy. Okay, you have to leave a pure gauge. That's the thing, and therefore the structure of the energy of the theory looks a bit like this. This is supposed to be a periodic function. Okay, so you have different theories around a particular vacuum. If you want to move to other vacuum, you have to, it costs you energy, okay? Now, if it turns out that this vacuum, that I've depicted here, that have a fixed winding number, Pontryagin index, let me just call it winding number because it's just so much easier for me. They are not gauge invariant, and they are not eigenstates of the Hamiltonian themselves. And this is because of the presence of instantons. Now, instantons can be depicted very simply here. Instantons are transitions between different vacuum. Okay. So this is an instanton, and this is another instanton, and so on. So instantons are histories that take one vacuum configuration of QCD, okay, and transform it, winding up the field to this other vacuum, okay? These are tunneling processes, and can happen at 0 temperature, okay? These are essentially tunneling transitions. And normally one computes these instantons. There are forms for these instantons, by the way. I brought you one. Instantons. Now these are here. Looks a little bit like what I wrote before, but these are not pure gauge objects anymore. And normally one works, this is the identity matrix. Bear with me just 1 second. Pauli matrices. Normally, instantons, so tunneling transitions are normally worked out in Euclidean path integral, right? So Euclidean path integral means we just perform a weak rotation, so we just change imaginary term, so time for imaginary time, and then the nice thing is that the potentials in the Lagrangian flip sign. So what something that was essentially forbidden in normal space or with real time, in imaginary time, it becomes allowed, and then one can just actually compute a path integral. So you have really a classical solution of the path integral that is this vacuum accelerates, goes up, and comes here, right? So this is a typical tunneling, the typical technology that we use to compute tunneling transitions. So this can be applied to QCD, and the results are these Euclidean path integral instantons. Like you can see here, they look a little bit like a pure gauge transformation, right? Because this G is an element of the gauge group, but here you have this instanton size. So this R is the radial coordinate from 0, and this rho is a particular constant, which is called the radius of the instanton. Okay. Yeah, yeah. So exactly. Yep. You can add more stuff here, but it's not going to change the winning number. That's the thing. So you need something. So this is the part that generates this winning number. That's why I'm sorry. Sometimes I. Sorry. Sorry? With what is this G? X? This one is the identity. X4. So this is yeah. So this is like time, but Euclidean time. Sometimes you write it as a fourth component. So I don't know, just tau or whatever.
For the sake of notation, sigma matrices are Gaussian matrices.
No, here I'm just using a subgroup, which are the Pauli matrices, and so far I have not. But you can write them. Yeah. So you can write the Pauli matrices in 3 by 3, right? Yeah, exactly. Yeah, exactly. Yeah. Exactly. Good point. So here you have some instanton. So these instantons, they take you to they jump from n equals 1 to n equals 2 and so on. Okay, but you can just concatenate different instantons, and if they increase the winning number, they're called instantons. If they decrease it, they call anti-instantons, and they can just be essentially they are just essentially flipping time here. And the important thing is that, well, as you see, I've found a configuration that takes one vacuum into the other, right? So just this should give you the idea that actually these vacuum are not eigenstates of the Hamiltonian, right? Because if I just can build a function that is going to take me away from this, so this state will not stay there forever, right? So already these instantons tell you that these objects are not the right vacuum to describe. And actually, the correct vacuum to describe this system are extremely generic. After all, they appear a lot also in condensed matter when you have periodic structures. These are called Bloch states. And they are essentially the theta vacuum, okay? Which are combinations. So let me just call each of these objects would be a state 0, 1, 2, etc. And I can build my theta vacuum like combinations of these states multiplied by a phase. This happens in many systems, right? Also, if you have a discretized, fields in one dimension, and the axion is just a massless field, you have just the gradient. So the axion is essentially the gradient, right? So you have to essentially, so the gradient couples nearby points, right? You can discretize if you want. Let us discretize the action, and then you find that the eigenstates are actually momentum eigenstates, right? So this is essentially like a Fourier transform of these fields, right? These different vacua combined with a particular phase, and this theta would be kind of the momentum, right, in this picture. So this one can see that these vacua are actually gauge invariant, and they are eigenstates of the Hamiltonian. So they stay there. That's the important thing. They don't evolve in time. Okay, so we have found something very interesting. So the way to describe the vacuum of QCD is just giving one value of of theta. You can see immediately, by the way, from here that theta is defined as a phase from 0 to 2 pi, right? If I change theta, if I go away from this interval, I can always just decrease it by a number of 2 pi, adequate 2 pi's, and this definition is not going to change, right? So I can just define it really as a phase in this interval. And something that I'm not going to prove because I'm already very late, is that when you just consider an operator, so the vacuum expectation, or the expectation value of an operator, this is an operator, in this vacuum, in the path integral formalism, this is equivalent, or let me just write it like this. This is a path integral, all the fields. This is the action, and here you get essentially another term. So you get these. Well, I'm going to write it just the full thing. So when you compute the expectation value of an operator in a theta vacuum, okay, you can do it with a normal path integral, with computing with the axiom that you wanted to use to weight your field configurations. But you have to add this term here, this extra phase. Okay, this extra phase. Now you recognize this object is n, right? It's an integer. It's actually coming from this phase. Okay, and this integer measures the change in winding number in a particular configuration, right? So path integral means you just put all the possible configurations with fixed initial and final conditions, right? And you compute these phases and you add them up, and then you just, the operator has to be here, of course. And you compute the operator weighted by these phases, right? Now, to compute it in the presence of a theta, so in a theta vacuum means that on top of the phase that comes from the axiom, you have to include an extra phase, which is the theta term multiplied by the winding number of your field configuration. Okay? So in practice, what we have found is that in order to take into account, so what we have found, what I'm telling you, is in order to take theta into account, right, it is equivalent to add to the Lagrangian a new piece. So we have, let's go here. So the Lagrangian of the standard model, or QCD, has to be supplemented by theta g tilde. There's this factor of the coupling. This is a normalization that I was just not displaying at any moment before. But here I put because it's customary. So actually, so this thing you already knew when you came here today, this morning. You didn't know that you knew this already, but Alex told you, right? It told you, okay, now I'm writing my the theory of the standard model, and I'm going to add all operators of dimension. Well, I'm just going to build it rationally, and I'm going to start with dimension 4 operators that respect all the symmetries that I have observed in nature. And then he started writing them, and he wrote this directly. He didn't torture you with homotopy classes or whatever. I'm sorry for that. But now you know. I hope that you know something else. I mean, this operator here is not only there because you can write it. It actually defines one particular possible QCD vacuum. So one theory of QCD defined by its vacuum is just given. So it's just equivalent to write this term here. Very good. You have questions? Why this does not apply? The thing is that the maps of you can do the same in principle, but you'll find that the homotopy classes of U1 in a 3-sphere is just the identity. So you can always, I mean, you don't have disconnected different possibilities. But so you cannot reduce. You cannot. So yeah, you don't have. So U1 is topologically trivial, right? In 3 dimensions. SU2 is the same than SU3. Yeah. Actually, so everything that I told you was for SU2, right? So in SU3 you have SU2 plus a lot of other generators, and these other generators do not change anything. So essentially, is that the dimension of the target space not the target space, the dimension of the physical space in which you define your gauge fields puts a limit on the complexity of the gauge group that you are. Exactly, we have SU2, and there, exactly in principle, there we have exactly the same issue, and we would define the same kind of vacuum. However, there's a subtlety there that I'm going to actually discuss now, next. Okay. So the question would be, why do I have to put this for SU3, but I've told you that it's the same for SU2, and I don't put it straight away for SU2, right? So that's a very natural question, and I'm going to discuss it immediately. So this part of the talk let's see if I just fit. This part of the lecture is called Revisiting the Phase Transformations. And the idea is that, or at least the U1 transformations, right? Remember that when a quark was transformed by gamma 5q, the Lagrangian didn't change. The Lagrangian, the kinetic term didn't change, but we had a change from the mass term, right? That if I do infinitesimal, so if alpha is just very small, you get, again, so the mass terms do transform. And now the anomaly brings a very interesting difference. Okay, remember that when I make a transformation of the fields, my Lagrangian changes according to the essentially to the divergence of the would-be current, right? So I've told you now that the divergence of this current at the quantum level has an extra piece, right? That comes from GG tilde. So when I make predefinitions of my phases, something has to happen now, right? So at the classical level, everything that I was doing before, just reabsorbing the phases in quarks, it was correct. But I know that at the quantum level, so if I take one loops into account, something is going to change. And in principle, I can just, this is the way I just mnemonically remember this, is that on top of this, you have to add the quantum contribution to the divergence of the anomaly, right? So you have now here is this. And here you'll have a number which is the anomaly, okay? So in this case, I'm transforming 4 phases, okay? I'm transforming the up quark right, the up quark right, the down quark right, the up and down quarks right. So I get essentially a factor of 4, so because these are the number of quarks that are running in my loop, okay? That's the idea. You have up, left, up, right, down, right, down, left. And each time I reabsorb a phase in one of my quark fields, I have one diagram that tells me, so the one contribution to the anomaly that I have to put in the Lagrangian, okay? So this, I find very easy to remember because of this. I find very easy conceptually to remember that when I change the Lagrangian, so when I make this transformation, the Lagrangian changes by the divergence of my current, and the divergence of the current, because of the anomaly, it has this contribution, right? So I find this very easy. But actually, one can prove that this comes from, one can prove strictly that this piece comes from the transformation of the measure of the path integral, okay? I'm not going to do it because it takes quite a long time for me, but I give you the way of thinking about it, and never forget that is this. Remember that when I make a transformation, my Lagrangian changes by the divergence of the current, and the divergence of the current at one loop includes the anomaly, okay? So remember what we did in the first lecture? At the very beginning, I wrote the Lagrangian of QCD with a phase. So I wrote the quark masses had mu, and I call theta lambda because it comes from Yukawa couplings, md. I wrote this piece, and I kept this phase for a couple of blackboards, and then I just told you, oh, don't worry, I can reabsorb it. Now you know that this is not the case. When I make a phase transformation to reabsorb this phase, immediately it reappears. So I absorbed here, I absorbed it here. So these are 4 phases that I'm reabsorbing, and they appear here. Okay? Because I made an infinitesimal transformation. So this delta lambda is nothing but the alpha parameter that I wrote before. So if I write my Lagrangian now, my Lagrangian of QCD with both phases, so it's kinetic term minus, let me just schematically write it like this, mq lambda and now I write, by the way, I prefer to have it with minus sign. if I write my Lagrangian like this, it's a function of these two phases. These two phases are potentially, both of them, CP violating, parity and time reversal. By doing transformations of U1, I can just change, I can reabsorb this phase, but it's going to appear in the GG tilde term. So it's going to appear adding up to the theta back. And the idea is, the following. So if I just transform alpha with the right, they appear here with a plus. So let me just put minus alpha, and this gets like this. Well, this is one of the most important equations of these lectures, so I'm going to write it very carefully. So I'm actually going to write this thing like this, and I'm going to write exactly what is the definition that I mean here of this alpha rotation. Okay, this Q goes to I alpha halves RL, RL, and alpha. Now I'm defining it like this. Because, I want to, okay, if I remove, so this means I take a small negative phase out of the right-handed quark. Okay, so here is going to remove a part of this phase, right? So it's decreasing. But when this thing is negative, this thing also becomes negative, and then it adds to the theta term that I defined negative. But okay. So now, and I put this half here, right? Motivated by the fact that when I have a phase here, I'm going to have a left and right phases. So both of them are going to appear. So this way, if I want to cancel theta lambda, I can just take alpha to be equal to theta lambda. And then it will appear here. So this tells you that this phase transformation can be used to change phases from the quark fields to the theta term. Okay, but you cannot make them unphysical. Okay, so this is very important because this phase of the quark mass matrix that before I just I just reabsorbed, now we know exactly that this cannot be removed, and actually we know something more. That sorry. It's here. So R and L, very good. Good. So, the factor of 2 is actually should be automatically included here, because here I made a transformation with alpha, so that's why I had to put 4. Sorry, but I prefer actually to do it like this. So when you change by alpha, here appears alpha. So you really have to put the 4. But I'm doing alpha halves, so that here I get really the number of quarks. So this tells you something very important, that is that essentially there's now in QCD only one. So I started with 2 phases, but with these phase transformations, I can always combine them in one right? So there's actually only one phase that is relevant, and this is called the magnificent theta bar. And this theta bar is equal to the theta of QCD. This is the one that defines the QCD vacuum. And then I have here this, so this is the phase of all the quarks, but I can just remove the phases of all quarks, and they all go here. When alpha is equal to the phase, so I get NQ times theta lambda. So this is theta bar, and is the only source of CP violation in the QCD Lagrangian. Okay, theta bar. Now, you will not see this equation written like this. You will see something which is a bit more obscure, but we are theorists, right? Instead of that, you will see that this is the argument of the determinant of the quark mass matrix. But this is essentially the same, right? Because if you just multiply all the entries in the quark mass matrix, you get the sum of the phases, right? Now, yeah, so, and then you take the argument, just the sum of all phases. Okay, so this is n times the common phase. And this is the theta bar, which is going to be the only source of CP violation. Very good. Now, let us solve the missing meson problem. Relatively fast because we didn't have much time. I'm going to do it in a physical way. So the idea is to, so I want to guess how is the fact that now I have in my Lagrangian, I have now a GG tilde term. And remember that without the GG tilde term, the potential energy for my mesons was mu v cube cosine, and then I'm going only to write the neutral sector mesons, phi 3 f minus m d v3, well, let's say the same for the so my guess is that there's going to be something new there. And what I want to do is to list the properties of this new term that comes from my GG tilde. Okay? So if the contribution from the anomaly, from the divergence of the current coming from quarks, produced me these terms on the Lagrangian, my new break is going to produce another one that is going to come from these instanton configurations, right? Because instantons are the field configurations that change the winding number, and instantons and variations of instantons are the only things that can contribute to GG tilde. That's why we say that this comes from instantons. Now, the first thing is that this object, principle, GG tilde, oh, sorry. Yeah. In principle, this object only knows about theta bar, right? Let me just, what I'm going to do, I've done this phase transformation so that theta bar, so that this phase, the common phase in the quarks, I've just reabsorbed the quark fields so that it appears in theta. So in principle, my potential would depend on the value of theta. But actually, you remember that in order to build this Lagrangian, this low energy Lagrangian, I have defined Goldstone-less quarks, right? I did something like this. I defined my quark with I redefine my quark fields to have explicit time-dependent phases, right? And this is a space-time dependent anomalous, U1 transformation, okay? So this is essentially the same transformation that I'm doing here, right? A rotation of the quarks, but now space-time dependent. Now, trust me if I tell you that you can do this, and it is exactly the same than doing, well, exactly the same, but you have to think about boundary conditions, but not very important. The important thing is that if I'm doing this, okay, I can use this master equation, and this tells me that when I'm doing this when I'm doing this transformation, this thing here that was my alpha, there's a gamma 5 here, that was equivalent to my alpha, now it's going to appear in GG tilde. So, yeah, so what I started with this, and I've done two transformations. First of all, I have just included the common phase of all quarks, and now I'm telling you that I want to reabsorb. I want to make this phase transformation, this field redefinition, sorry. So now what I'm getting here is twice the eta field multiplying GG tilde. Or at least, if you want, this I'm doing it for the full field because it's interesting, but if I do it for the vacuum expectation value, you would have no problem about it. So actually, now you see that this object here, the potential generated by instantons, it has to depend on theta bar plus twice the pi field divided by f. Right? Because it's what appears multiplying GG tilde. GG tilde doesn't know anything else about the rest of the theory in principle. Very good. So it has to depend on this object. It has to be periodic because we know that GG tilde, it appears, so if we integrate, so when it appears in the action, it appears as a phase. Remember that everything is periodic in theta, so everything should be periodic in this quantity as well. So this means that, theta, so this potential as a function of x is the same potential plus 2 pi, and so on. So this is the next equation. And then the most important thing, so first of all, the potential is periodic, like these cosines. The potential depends on this variable and not on any other combination. Then there's another, the most important perhaps, quantity, that is the quality, that is what tells you the Buffer-Witten theorem, that tells you that actually, and the most important thing for these lectures, is that this potential has a minimum at x equals 0. And this can be easily proven in a path integral. I'm not going to do it, you are going to do it, but I'm going to write the path integral. With my notes. I'm writing in Euclidean, and this is the potential, okay, as a function of, now x, sorry for the, well, let me just call it phi. This phi is now this combination, of course, or I can call it theta. By definition, this is just the path integral, all the gluon fields, etc. The Euclidean action, it depends on the gauge fields, etc. And then here you have the theta term. When you go to the Euclidean, when you do the weak rotation, the normally, so this phase becomes a real number. But something very important here, with the theta term, it does not. So one thing to think, so you can try to, if you understand what I'm talking about, please think about this as a little exercise, why this thing is still imaginary. So try to do the weak rotation to this term and see that this is still imaginary, and this is very important. Weak rotation. This is very important because this precludes us from doing lattice calculations at theta, at a value that theta is different from 0. Because we use Monte Carlo, so the Monte Carlo techniques that we use for sampling the path integral rely on this thing being positive. Now, if this thing is an imaginary, this means that this oscillates very fast, and then the techniques that we have, they are worthless. So this is called the sign problem of lattice QCD at finite theta. It is an important issue in lattice gauge theory. So think about this. But so if I'm telling you that this is the potential, this is what defines the potential, you immediately can also find from this definition of the path integral that the potential at 0, at theta equals 0, is smaller or equal than the potential at any other value of theta. Okay? This comes from this expression essentially all together, and is left as an exercise for you. Buffer Witten. And it's just simply using the triangular inequality. So for those who listen. So then we have the third condition here, and most important, that B at 0 is the minimum. Absolute minimum. So then I'm going to do a wild guess, because actually this is not so important for the results, for the rest of the results of the talk, and I'm going to write that this potential is like this. Okay, so cosine, this cosine is periodic. It has a minimum when this quantity is equal to 0. It's the absolute minimum. And it depends only on this combination of theta bar and the eta. Okay? And now, this lambda to the 4 is just an energy scale related to QCD. I'm going to guess that is of the order of the confinement scale of QCD, and actually this is what is the natural scale, because the gluons, they confine with a typical density of 1 GeV to the 4, so I'm going to expect that this is 1 GeV to the 4th, and indeed this is going to give us more or less the right order of magnitude for the eta prime mass. Because now you can immediately, with this Lagrangian, you immediately see that the eta, or the missing meson problem is solved, right? Because this quantity here, now, it is not related to pion masses or anything. This is related to hardcore QCD, confining QCD to gluons, okay? And this can be much larger than the quark mass multiplied by the quark condensate. So that the eta prime can take most of the mass, actually dominant contribution from the mass, from this potential. So if you want, I will do the exercise, but it's not very important. So now all that we would need to do from this potential, which is also very important for the rest of the lecture. I don't know what to write, where to write, no? Still have 6 minutes. So okay, we have built a best guess for this potential, and you can immediately compute. You can do it yourselves, but if you want, I can do it we can compute the mass matrix around, so you can just find the minimum of this potential, compute the mass matrix, and you'll find that there's one mass that can be set by adjusting this parameter, and so on. But the important thing there is not that we can solve the mixing meson problem, is that we have introduced a new CP violating variable, which is theta bar, a constant, that is theta bar, that is going to be CP violating. And this introduced strong parity and time reversal violation. Theta bar is going to create issues. So let me just show you how this happens. Or better not. No, let me just tell you that, because this is relatively involved and I think I'm going too slow. Let me just tell you that this, so if theta is different from 0, you are going to generate observables that are CP violating. No surprise, right? One of the most important ones is the electric dipole moment of the neutron, and one can compute that this is of the order of 2.4 10 to the minus 3 electron charge times femtometer. There's a nice calculation that can be done that gives you essentially the same result. And this calculation comes from, as you will understand immediately, so the neutron, I'm talking about electric dipole moment. So I start with a neutron and I have to extract a photon. And what I do is converting the neutron into a proton by sending, by emitting a pion, okay? And the structure of the theory now that I have CP violation, what you can imagine that is what is going to happen, right? So the theta bar is going to appear in the couplings of my mesons and in the between themselves and with mesons, okay? I'm not going to bore you with details, but yeah. You can see essentially that in this calculation, the CP violating coupling can appear, a CP violating coupling can appear in any two contributions. It is what is called the coupling of pions to nucleons, but CP violating. And this thing here is proportional to theta bar, okay? Times theta bar. And actually, okay, so this calculation can be done. I'm not going to do it, but now that I have a CP violating phase in my theory, it propagates essentially to many couplings. So for you, it should be natural that things like this can happen. If you want, I can give you more details, but not now. The important thing is that, look at this. So this is the dipole moment of the neutron. So neutron is just a ball of quarks and gluons, right? And if QCD would be parity and time reversal conserving, the quarks that have electric charge, they would be distributed, or the wave function of the quarks, it would be distributed in a parity and time reversal preserving way, okay? But if the interactions of gluons and quarks are not parity and CP conserving, because theta is different, theta bar is different from 0, now my quarks can be distributed inside of the neutron in a CP violating way. And since quarks, they have charge, electric charge, this electric charge is going to be distributed in a CP violating way, which is essentially what is happening here. So the neutron can have its charge distributed in the form of an electric dipole moment. And an electric dipole moment violates parity and time reversal, as probably you know, but I can tell you later. So the strong CP problem comes when somebody does this calculation, and what you get here, I just expressed it in natural units. The size of a neutron is more or less the size of a femtometer, right? It's 1 inverse GeV, something like this. So a neutron is a sack of quarks and gluons of the size of 1 femtometer. Quarks, they have charges which are of the size of the electron charge, okay? So this would be the natural size of an electric dipole moment if the quarks would be completely separated in charge, right? If you just put all the 2 up quarks, you just put them separated from the down quark. This 10 to the minus 3 is a suppression that comes from a loop, but I will explain you that it has also another origin or a different way of understanding. It's this slight suppression. And then, of course, it has to be proportional to theta bar, right? Now, the interesting thing is that people have tried to look for this electric dipole moment of a neutron, and they have found that it's smaller than 2.6 or something times 10 to the minus 13 or so. I don't even have the number. So this is an experimental number, which I should know very well. But this means that, no surprise, QCD respects CP. To the best of our knowledge, this is what we started when we started understanding the strong interactions, and this is where we stand now, up to today. So we have not found any sign of CP violation in the strong interactions, and this is what one of the most exquisite measurements of our degree of knowledge that the strong interactions respect CP, because it implies that theta bar, it has to be roughly smaller than 10 to the minus 10. Which is a very small number, right? But it's not only a small number. So this would be a small number, but this number is the sum of 2 numbers. Remember? Theta bar is theta plus the argument of the determinant of the quark mass matrix, right? And we have observed CP violation in nature, right? In the electroweak interactions. This CP violation comes from where? From CKM matrix, which in the standard model comes from the Yukawa couplings of the Higgs with quarks, right? So the Yukawa couplings of the Higgs with quarks, they have phases in such a way that when you build the CK matrix, you get a phase. And this phase, do you know more or less what is the size of this phase? Well, it's something like 60 degrees. So it's a large phase. Not that this phase is very small. Okay, it's a phase of order 1. And here we have something which is 10 to the minus 10, which is the sum of 2 things. One of them we would expect this to be 1, and the other one is something that God, when he decided what theory of QCD we are going to suffer, decided is going to be something, right? Perhaps, or some. Well. So the sum of these 2 things has to be smaller than 10 to the minus 10. This is a very interesting puzzle, theoretical puzzle. That's why sometimes this strong CP issue is called the strong CP problem, because we expect theta bar to be of order 1, and we have found this amazing result. So yeah, tomorrow, I wanted to do it today. Tomorrow I will explain. Finally, we will meet the axion in a very straightforward way. Now everything is much simpler. So because I have introduced essentially all the ingredients that I'm going to use in the rest of the lectures. The anomalies, Goldstone bosons, the potential, minimization of the potential, quark masses, and so on. So it was a long and tedious road until today, but from now on, everything's much smoother. Thank you very much.